We are looking at section 5.8, which is continuation of substitution. Pretty cool stuff. This section's introducing the transcendental functions that we didn't have to deal with in the previous section. Other than that, it's pretty much a carryover from 5.7 questions. This first question is trying to get us accustomed to doing the algebra that's required in some of the problems, where it's asking us to work with 1 over 4x squared plus 9. And it's wanting us to force out a factor of k so that the 9 in the denominator becomes a 1. So obviously, if I need that 9 in the denominator to become a 1, then I'm going to have to factor out a 1 over 9 in order to ensure that. Now, when I factor that term out, it not only factors out of the second term in the denominator, but it also factors out of the first term in the denominator. So I would have 1/9 times the fraction 1 over 4/9 x squared plus 1, and that's equivalent to the original. Now, the u substitution I would make, because this is going to be some form of an inverse tangent integral, where if this were the term on the inside, but inverse tangent is 1 over x squared plus 1. So we would say, well, we need this to be 1 over a variable squared plus 1. So I would just let the variable u squared equal 4 over 9x squared. Thus, when you take the square root, you can say, well, u would equal the positive or negative square root of 2/3 x. Typically in problems, we just do the positive root. They're both correct, but for this problem, it's going to want you to put both answers. And unlike what I have here where I have plus and minus, notice it says in the directions use a comma separated list. So it will want 2/3 x and then comma negative 2/3 x. Now, for the value of k in this problem, the value of k was what value that you pulled out in front. So clearly that's my 1/9. I'll go ahead and show that here. 1 over 9. And then for the second part of this, the value of u, that's where I'll say, well, it's negative 2 over 3x. Whoops, not the x in the denominator. And said to separate with a comma, and then 2 over 3 times x should be what they're wanting for this algebraic simplification. And it is. Now, the second question is going to lead you into a very helpful video here of how to work. This would be some version of an inverse sine function. It's wanting you to get it into the format of 1 over the square root of 1 minus t squared, so that you can say that this is the inverse sine of t. And they're just going to be discussing how to do that in the video. Very good problem to be looking at. But now, for the purposes of this video help session, I'll keep on going. The next question, awesome. It's asking us to integrate 13 over 81t squared plus 25 with respect to t. So first thing I have to do is recognize anytime I have a constant divided by a variable squared plus a constant, I'm thinking this is some version of the inverse tangent function. So 1 over t squared plus 1 is the inverse tangent of t. I don't have that, but I have some version of that. In order to see my answer, what I do first and foremost is I factor the 13 out of the numerator and the 25 out of the denominator. I need to get that constant to be a 1. So once I factor out 13 over 25, my denominator is 81 over 25t squared plus 1. I need to let u squared in that place right there, then this will be the inverse tangent of u. So I need to let u squared equal 81 over 25t squared. Take the square root, u is going to be 9/5 t. And then I can say, well, then the derivative of u would be 9/5 times dt. In order to do this substitution, I had to see a 9/5 dt on the inside. So I had to multiply it from this step to this step. I had to multiply by 9/5 on the inside, which means I had to multiply by 5/9 on the outside. Now this 9/5 dt, we know becomes du. That's where that came from. And the rest is just going to become 1 over u squared plus 1, which by definition is your inverse tangent of u. So when I integrate this, I'll get inverse tangent of u plus the constant of integration. When I simplified the factors that I had on the outside, I got 13 over 45. Final answer here, when you substitute back in for u is equal to 9t over 5, or you could write it as 9/5 t. I kind of like 9t over 5 better, so that's the way I'll enter it in. We get 13 over 45 inverse tangent. I'll go ahead and put this in here, 13 over 45, and then we have, whoops, inverse tangent, and I'll need to scroll back so I can raise this to the, it looks like to the -1 power, but hopefully it'll understand that that's inverse tangent of 9t over 5. And then plus our constant of integration on the outside of the group should be exactly what they want. So I'll go on up here and check this answer. And it likes it. Okay, so now up next here, guys, for number 4, very quick question. It's a little strange one. I don't like this one very much. It says rewrite the function y equals 6x to the 6th in terms of u, where u is 7x to the 6th. So think about that. If u is 7x to the 6th, but then I'm trying to rewrite y in terms of u, and y is 6x to the 6th. Well, I know 6x to the 6th is the same thing as 6 over 7 times 7x to the 6th. This would give me my 6x to the 6th back. But then 7x to the 6th is u, so I know y is equivalent to 6 over 7 times u by substitution. That'd be my final answer. Y in terms of u is 6 over 7u. More of an algebra question than it is a calculus question, but that's okay. For the next question, it's one of these where you're going to get credit by watching a video. This one, it's going to have an exponential function divided by an expression that contains an exponential function. It's going to discuss how substitution is going to simplify that integral. So please do watch that. But now let's go ahead and work a problem that deals with that. And this one is much more difficult than their example there. So for number 6 here, I have 8 times the integral, the integral of 8 times the exponential function, 5 to the x, and we're dividing that by 12 plus 5 to the x. So, okay, in order to simplify, I'll go ahead and let u equal that denominator, 12 plus 5 to the x. I know the derivative of 12 is 0. The derivative of 5 to the x is 5 to the x times the natural log of that base of 5, and that's with respect to x. So now, in order to do this substitution, I literally need to see a 5 to the x natural log of 5 dx in the problem. I have the 5 to the x dx in the problem, but I don't have a factor of the natural log of 5. So in the next step, all I did is I multiplied by that natural log of 5 on the inside. So I'd have 5 to the x natural log of 5 dx. In this step, I've multiplied by natural log of 5, so I need to divide by the natural log of 5 on the outside. And you'll see the other thing I did here is I just factored the 8 to the outside. So now I have 8 over natural log of 5 times this expression. In this expression, that entire numerator along with the dx is going to become du. So I'm left with just 1 over my denominator, which is 1 over u du. We know that the integral of 1 over u du is the natural log of the absolute value of u. And then I can say, well, all right, when I substitute u back in, I don't even need the absolute value anymore because 12 plus 5 to the x is guaranteed to be positive anyway. I'll have 8 over natural log of 5 times the natural log of the group, 12 plus 5 to the x, plus your constant of integration. I try entering that in here, 12 over the natural log of 5, and then we have times the group, and I'll not say times the group yet, it's the natural log of the group, 12 plus 5 raised to the x power. And then we just get out of that parenthesis and say plus the constant of integration. This should represent the answer that they want, assuming I've typed everything in correctly. And it does. For number 7 here, we're asked to evaluate the integral from 1 to 4 of dx divided by 7x. This one's very quick. All I need to see is that that 7 in the denominator can be factored to the outside as 1/7. And then I just have the same thing as 1 over x dx, which I know the integral of 1 over x dx by definition is our natural log function. This is the exception to the power rule. We say, well, anytime x is to the -1 power, it's the natural log of the absolute value of x. And we're evaluating this from x equals 1 to 4. So we're going to get 1/7 the natural log of 4, and then minus the lower limit of integration, 1, minus the natural log of 1. Natural log of 1 is 0. So we just get 1/7 the natural log of 4, final answer. And keep in mind, you really didn't have to put the absolute value here since both of your limits of integration were positive anyway. Didn't impact the answer in any way though. 1/7 the natural log of 4, final answer. Number 8 here. It's a very, very, very similar problem, except now we have a limit of integration that's an exponential function. That doesn't make it any harder. Same thing I did in the last one where I factored the 7 out. This time I'll factor the 5 out. I know that the integral of 1 over t with respect to t is the natural log of the absolute value of t. I'm now evaluating that from 1 to e to the 4th. And so then again, I don't need the absolute value. I can just say it's the natural log of e to the 4th minus the natural log of 1, which I know is 0. All of this being multiplied by 1/5. Well, natural log and e are inverse functions. They cancel and would just give me 4. So the inside I have 4 minus 0. That's 4 minus 0 times 1/5. Final answer of 4/5. We check that answer and Achieve says absolutely. For the next one here, number 9. We have the integral from 1 to 11 of dt over 4t plus 6. So yet again, this is going to be a natural log, but takes a little bit more work to get to it. So this time I had to do the substitution. I'll let u equal the denominator, 4t plus 6. The derivative of that is going to be 4 with respect to t. So now in order to do this substitution, I have to see a 4 dt in the problem. I multiply by 4 on the inside, right here, divide by 4 on the outside. Right now, all of this is still in terms of t. But to go from this step to this step, I want to put it in terms of u and use that 4 dt to become du. Then I'll have 1 over u du. In order to do that, though, you have to change your limits of integration. You say, well, u evaluated at the lower limit of 1 gives me 4 times 1 plus 6. That's where the 10 came from. U evaluated at the upper limit gives me 4 times 11, 44, plus 6 is 50. So now I'm integrating from 10 to 50 of 1 over u du. That gives me the natural log of u evaluated from 10 to 50. That's the natural log of 50 minus the natural log of 10. And I know whenever I have a minus, I could condense that to one logarithmic term and say, that's just the natural log of 50 over 10, natural log of 5. I would write my final answer as 1/4 natural log of 5 here. And we'll see if Achieve likes that. And they do. Up next here, you see we're kind of breezing through this section. We're already on number 10 after not much time at all. And there's, I think, 33 questions total, but the questions get more fun as we go. Number 10 here, this one's pretty straightforward, pretty quick. I see, hey, the inside is 1 over x squared plus 1. That is defined to be the inverse tangent of x when we integrate. But we'll say, well, it's the inverse tangent of x evaluated from the lower limit of the root of 3 over 3 to the upper limit of 1. And I said, well, that's just the inverse tangent of 1 minus the inverse tangent of the root of 3 over 3. And now we're expected to be able to get these values from our trig knowledge. Inverse tangent of 1 is just asking you, when is your tangent function 1? Tangent function is 1 at pi over 4 because the ratio of sine to cosine is 1. So, well, the inverse tangent of 1, pi over 4. What is the inverse tangent of the root of 3 over 3? That is asking you, when is the ratio of sine to cosine the root of 3 over 3? And you say, well, that's at pi over 6. Because at pi over 6, the sine divided by the cosine would be 1 over the root of 3. Well, 1 over the root of 3 simplifies if you rationalize it to the root of 3 over 3. That's at pi over 6. So you can say, and you might have just thought, okay, the inverse tangent of any number less than 1, the only time the inverse tangent has an argument less than 1 is an angle less than pi over 4. The only angle less than pi over 4 we're supposed to know in quadrant 1 is pi over 6. Had this been the inverse tangent of the root of 3, well, then it would have been up here at pi over 3. There's only these 3 values that we're supposed to know in each quadrant. So now I can say, well, this is just pi over 4 minus pi over 6. I get to my pi over 12 final answer. And please note, it does want exact notation here. So we don't want any wimpy decimals. Pi divided by 12 should be our final answer. Correct. Up next here, we are supposed to evaluate from 0 to 1/2 of dx over the square root of 1 minus x squared. Again, no work to do. It's automatically, that's the inverse sine function when we integrate. But now it's more of a trig question because we have to evaluate the inverse sine of x from 0 to 1/2. Inverse sine of 1/2 minus the inverse sine of 0. The sine function is 1/2 at, I think I made a mistake here. I put pi over 6. No, that's right. That's not wrong. I think I made a mistake. I didn't make a mistake. The y value on the unit circle is 1/2 at pi over 6. So the inverse sine of 1/2 is pi over 6. And then minus the inverse sine of 0. You say, well, when is the sine function 0? At 0. So correct, I get pi over 6 minus 0 for an answer of pi over 6. I started to think that that first one was pi over 3, but that's the inverse cosine of 1/2. So I'm getting pi over 6 for my final answer here, and I'll have to go down and use their pi over 6, and we'll say, oh, that's a piece of cake. Yeah. Up next, we have the integral from 0 to 8 of dx over x squared plus 64. So finally, you're thinking, okay, there's going to require some more work in this one because this is not just the straightforward inverse tangent function like number 10 was. So I'll have to do some substitution work to make this the more straightforward inverse tangent. So the goal of substitution is to always take something that doesn't fit our standard basic rules and turn it into something that does. So I want to end up with 1 over u squared plus 1. So I can say, well, that's just the inverse tangent of u. In order to do that, I need to get that 64 out of the denominator. So from this step to this step, just factored out a 64 in the denominator to get 1 over 64 times this group. Now the x squared term is 1/64 x squared. So I let u equal 1/64 x, or u squared equal 1/64 x squared. Take the square root, so u is equal to 1/8 x, and then du, the derivative of that, would be 1/8 dx. Now I can say, well, all right, in order for this substitution to be done, I need to see a 1/8 dx in the problem. I did. I multiplied by 1 over 8 on the inside. If you multiply by 1 over 8 in the inside, or if then you must multiply by its reciprocal, 8 over 1 on the outside. This makes up for what I did here. Now on that outside, you're going to get 8 over 64, which simplifies to 1 over 8. The 1 over 8 dx, we know, becomes du. So I'm going to have 1 over u squared plus 1, since I know u squared is the 1 over 64x squared. 1 over u squared plus 1 du. And now my new limits of integration have to be in terms of u. I show where they come from here. Evaluate u at the lower limit, you'll get 1/8 times 0 is still 0. You evaluate it at the upper limit, you'll get 1/8 times 8. That's why the upper limit is 1. So we're evaluating the integral from 0 to 1 of 1/x² plus 1. It gives me the inverse tangent function evaluated from 0 to 1. And I can say that's the inverse tangent of 1, pi/4, minus the inverse tangent of 0, which is 0. 1/8 times pi/4 gives me pi/32 for a nice answer. And I'll go in here and say, palette, please help. Pi divided by 32. Check that answer. And it likes it. Okay. Coming up next, we have to integrate dt over the square root of 1 minus 36t to the second. As soon as you look at this problem, you're supposed to be thinking, okay, this is some version of an inverse sine or integral, because the inverse sine would be 1 over the square root of 1 minus t squared. That'd be the inverse sine of t. So I have that 36 in there. Well, all right, that's in the way. So allow u squared to equal 36t squared. Take the square root, u would equal 6t. Therefore, du is 6 dt. In order to make this nice substitution, you have to see a 6 dt in the problem. I don't, so I can say, well, I can multiply the numerator by 6 to get to 6 dt if I divide by 6 on the outside. Now this becomes 1/6. That numerator just becomes du. Your denominator, the whole point for doing this was now it's going to become the square root of 1 minus u squared instead of 36t squared. So that, by definition, is the inverse sine of u. I'll have 1/6 the inverse sine of u plus the constant of integration, which now, once we know u is equal to 6t, we can say this is just 1/6 the inverse sine of 6t plus the constant of integration. And we'll type that in up here, 1/6. And then we have inverse sine of 6t plus c. Now I haven't forgot the inverse. I'll go back and do that. It's not the sine, it's the inverse sine. So I will raise that to the -1. That's really not the next sine to the -1 power. That's going to stand for the inverse sine. And we'll check that. And they like it. For the next one here, number 14. Let me scroll down through here too. We have the integral of dt over the square root of 5 minus 7t squared. Just like the last problem, as soon as I looked at it, I knew the answer was going to involve an inverse sine. You need to know the answer this time also involves an inverse sine because it's a constant divided by the root of a constant minus a variable squared. In order to get this in the nice format, first thing I would like that constant to be 1. So you'll see the first thing I did is I factored out a square root of 5 in the denominator. I get 1 over the root of 5 times this fraction on the inside. My numerator is the same. My denominator is going to be the root of 1 minus 7/5 t squared. Now I don't like that 7/5 t squared, so I'm going to let u squared represent it. By using that substitution now, I'll say, well, u is the square root of that, which is going to be the square root of 7/5 times t to the first. And then du is just going to be the square root of 7/5 times dt. Now, in order to carry out this substitution, I have to see this square root of 7/5 dt in the problem. I don't have it, so I had to multiply by that on the inside, which means I had to multiply by its reciprocal on the outside, or you could just say you had to divide by that on the outside. Now, on the outside, I see that the root of 5's cancel, and I'll have 1 over the root of 7. The inside portion, the whole reason for having that is I wanted to replace it with a du, so I did. And now my denominator is the square root of 1 minus u squared. By definition, that is the inverse sine of u. So I'll get 1 over the root of 7 times the inverse sine of u, where I already know u is this right here. Now, I wrote this as the root of 7 times x over the root of 5. I kind of like the way that looks better. as the argument inside the inverse sine function, but it doesn't matter. You could have left it the root of 7/5 times t in there. I'll go ahead and input this answer in, and I'll need the palette that they have. So I'll say 1 divided by the root of 7. And then we had this times the inverse sine of t. I'll go ahead and say sine, and I'll raise that to the -1 here. And my angle was, again, a fraction. I'll go ahead and put that fraction in there. And the numerator was the root of 7. So root of 7, arrow out of the root, times t. My denominator had the root of 5. This problem's a little bit more difficult to enter in and make sure you get it right. I think I've represented what I have. Let me pull back up my answer and just double check. 1 over the root of 7, inverse sine of the root of 7 times t over the root of 5 plus your constant of integration. Glorious. We'll check that answer, and they like it. Up next here, guys. So the next few problems aren't actually quite as fun as that one. The exponentials in this section, they don't get that bad. And in this one particularly, if you use substitution to simplify, it really makes things nicely. We have the integral from negative natural log of 4 to 0 of e to the 2x dx over 1 plus e to the 4x. So automatically, what I did is I said, well, what if I let u equal that exponential function to the 2x power? So then the derivative of that would be 2 times that exponential function. Please remember, derivative of any exponential function is that exponential function times the derivative of its exponent. So the derivative du is equal to 2e to the 2x times dx. Now, I already have almost all of that already up here. I have e to the 2x dx. The only thing I needed was that additional factor of 2. So I multiplied the numerator by 2, divided the outside by 2. Notice I left my limits of integration and everything else the same. The only other thing I did here was just to show you, and this is an algebra maneuver, to remind you that that e to the 4x in the denominator, it's the same thing as an e to the 2x quantity squared. So now I'll be able to write that as u squared whenever I do my substitution. Gorgeous there. Now, in preparation to do that substitution, you need to go ahead and change your limits of integration. U evaluated at the lower limit would be e raised to the 2 times the negative natural log of 4. So that's the -2 natural log of 4 power on that exponential function. I know that any coefficient of a logarithm can go up as an exponent, so I have e raised to the natural log of 4 to the -2. Now e and natural log are inverses, so they cancel. So I just said, well, this is just 4 to the -2, which means 1 over 4 squared, 1/16. Now, when I evaluate at the upper limit, it's just e to the 0. E to the 2 times 0 is e to the 0, which we know is 1. So we're evaluating this integral from 1/16 to 1. Our denominator simplified to be 1 plus u squared. Numerator all canceled out because it was equal to du. By definition, that's the inverse tangent of u. When we integrate it, we'll have 1/2 inverse tangent of u evaluated from 1/16 to 1. Inverse tangent of 1 is pi over 4. Inverse tangent of 1/16 is not a number that is one of our standard values on the unit circle. So we just leave it as it is. And we should say this is the exact final answer. And they do not want a decimal approximation. So this is the answer that they'll request. I'll say, well, okay, I have 1/2, and then that's 1/2 times the group. The first term inside of that group is going to be pi over 4. So I'll come down here to my palette and say pi divided by 4. And then after that, we have minus the inverse tangent. So pi over 4 minus the tangent, and I'll go ahead and say inverse tangent using the -1 power for inverse of 1 over 16. That should be our final answer. Again, of course, remember there is no plus c since this is a definite integral. And we got it. Up next here for number 16, pretty quick question. It gives us the integral of the inverse tangent of x quantity cubed divided by 1 plus x squared. And we say, well, all right, I know that the derivative of inverse tangent of x is 1 over 1 plus x squared. So as soon as I see that 1 plus x squared in the denominator, that's kind of a dead giveaway. Hey, I want to let u equal what's inside of that group in the numerator. Let u equal the inverse tangent of x. Then the derivative du is 1 over 1 plus x squared with respect to x. I need to understand this could be rewritten as the inverse tangent of x to the third times 1 over 1 plus x squared dx. All of that last product all becomes du. The only other thing in there is you have the group cubed. That's going to become u cubed. So now the integral of u cubed with respect to u, power rule says u to the fourth over 4. Now back substitute, we know u was the inverse tangent of x. Final answer is just going to be 1/4 the inverse tangent of x raised to the fourth power plus c. Now be careful that you make sure that that 4 is on the entire inverse tangent function and not just on the argument within it. So I'll need to make sure I account for that correctly. I'll go up here and say I have 1/4, and now it's 1/4 times the group where we have the inverse tangent. I'll go ahead and say that that's raised to the -1 power for the inverse tangent. And we have of x, get out of the argument, get out of the inverse tangent function, raise all that inverse tangent to the fourth power, plus your constant of integration should be good. Yeah. Next question here, number 17. This one's kind of, well, not kind of, very anticlimactic. Not fun at all. It's just an exponential function. We know integral of any exponential function is that exponential function divided by the derivative of its exponent, which is 1, times the natural log of its base, ln 7. Integral of 7 to the x is just 7 to the x over ln 7. We're now evaluating that from 0 to the log base 7 of 5. So I can say, well, all right, then it's 7 raised to the 7 log base 5 minus 7 raised to the 0. All of that's divided by the natural log of 7. My numerator, these two, exponential base 7, log base 7 cancel, so the first term is just a 5. Any number to the 0 power is 1. So my numerator is going to be 5 minus 1, or 4. Final answer, 4 over natural log of 7. And check that. And they like it. Couple more for this video before we do a break for the second portion of this section. For number 18 here, I want to look at the integral of 10x times the sine of, I should have said 10 to the x, times the sine of 10 to the x with respect to x. So I know I cannot integrate any trig function with an exponential on the inside. That doesn't fit our standard integration rules. But what I can do is I can say, well, I can use substitution here. If I let u equal what's inside of that sine function, I know that the derivative of any exponential function is that exponential function times the natural log of its base with respect to x. Now, in order to carry out the substitution in this, you have to see all of that in there. Well, we see a 10 to the x dx. We just don't see the natural log of 10. So I multiplied it as a factor in this second step on the inside, which means I had to divide by the natural log of 10 on the outside. Now, from here to here, 10 to the x, natural log of 10 dx, all became du. This is just the sine of u. We get the sine of u du integrated. You can say, well, the integral of the sine of u is going to be the negative cosine of u. Now that negative can go out and multiply the 1 over natural log of 10 and give me -1 over natural log of 10. And then I'll have times the cosine of u, which we know is 10 to the x, plus our constant of integration. So now inputting that in, we'll get -1 divided by the natural log of 10. And then that's times the cosine of 10. And we know that that was an exponential function raised to the x power, plus our constant of integration. And last problem I'll do in this video, I will handle the remaining problems in one more video for this section. Number 19, I have the integral 6y times the exponential function e to the 2y squared dy. This problem, similar to the one before, except now I want to use substitution to account for instead of the angle of my trig function, I'm going to let it be what's inside of my exponential function. I'll let it be this 2y squared. If u is equal to 2y squared, then du would equal 4y dy. Now, I needed a 4y dy in order to carry out the substitution in this problem. I see a 6y dy in there. Well, I know the 6 isn't helpful, so what did I do? I just factored out a 6. That's where that 6 came from. But now I need to multiply the inside by 4, which means I divide the outside by 4. Please make sure you understand, though, that what I have is equivalent to what I had. You could easily convince yourself of that by saying, oh, okay, if he distributed this 6 over 4 times 4, it's the same thing as the original having a 6 on the inside. Absolutely. But now in this format, I can see that the 4y dy are going to become the du in the next step. The e to the 2y squared, that's just going to become e to the u. So I get, outside simplifies to be 3 over 2 times the integral of e to the u du. Integral of e to the u is e to the u plus the constant of integration. I multiply that by my 3 over 2. Substitute back in for u, and you'll get 3 over 2 e to the 2y squared plus your constant of integration. We'll try that for our gorgeous final answer there. 3 over 2 times the exponential function e raised to the 2y, and then the y is raised to the second power. And we'll say plus our constant of integration there. And they liked it. All right, guys, I'll stop with that for this first portion of 5-8. You'll notice it took me 3 problems for the first 19. It took me another, 3 pages for the first 19. It took me another 3 pages for the remaining 14 problems. So not much longer, but they get a little bit nicer than these opening problems. But you'll just need to catch my second video for this section to catch problems 20 through 33.